a little bit what is the setup that we did yesterday. So we made a choice of asymptotic states to scatter, and we chose that our particles are scalars only. There is only one single scalar in the IR, so that's our theory. There is like a symmetry, 5 goes to minus pi, some Z2 symmetry, this particle Z2 even, and then mass equal to 1. So that pretty much fixes you what is your asymptotic Hilbert space. Then we introduce the set of observables, which are these S matrix data, which are real numbers. And these real numbers, if you know all of them, they uniquely identify the amplitude. Is T of STNU, where STNU are the Mandelstam invariants. And this function STNU is fully crossing symmetric because of the choice of asymptotic state. Then we introduced one of the most important constraints, but it's not the only one. And today we'll discuss another constraint, which is unitarity. And we also mentioned that unitarity in general can be relaxed to an inequality. And the inequality comes from the fact that the imaginary part is equal to absolute value squared, like the optical theorem if you want. It's equal only if you only scatter two particles that go into two particles. If only on shell, you can have two particles into two. But then when on shell, you can also put four particles in final state. That's where the inequality kicks in. Because we drop all these multi-particle outgoing states, because it would make the problem much more complicated. We still don't have the technology to go there fully. But we can keep the inequality. And that's a rigorous constraint. In the sense that our space of amplitudes might be smaller, but for sure will be contained inside this convex region. And this constraint is convex. And that's basically the reason why this figure that I mentioned yesterday, today we will talk more about this figure, which you plot on this axis C00 and C10, these two S matrix data. That constraint is convex, that's why this figure is convex. The two amplitude space might be much more complicated. You know, might be something like this, the true amplitude space. We don't know. Because the true amplitude space has to satisfy all the multi-particle constraints. But what we know for sure is that these are surely consistent, and then if we add more constraints, we can perhaps do even better. So, but we start somewhere, which is there. Then, other important factors, at least for the 2 to 2 amplitude, are the let's say S matrices, the partial wave S matrices, which are just given by 1 plus I, the partial wave f of the amplitude. And if you do like this, unitarity obeys this very nice form, which is like it's like a probability conservation. And then another parameterization that we introduced yesterday at the end is that the S matrix can also be written as like the exponential of some complex space, which is real when we have the equality here or the equality here, or in general it's complex. And then unitarity is stated the imaginary part of this space must be positive. Because there are different ways to impose unitarity. And well, and here I just write, well, what is rho? I remind you that rho is this factor, it's a phase space factor, that I want to point out that in generic d-dimension, in d greater than 4, let's say this factor grows, and this will have some consequence for the bootstrap if you study scattering in higher dimensions than 4. And in general, the partial wave, I wrote it here for you, it's just the partial wave projection in any dimension. Which the only things that change is that there is some additional kinematic factor here. And instead of the Legendre polynomial, you have Gegenbauer polynomials. But this is just to say that everything is under control even if you go in generic dimensions. And you could repeat the same exercise. Actually, some people did it recently. Okay, so we were here yesterday. Now today, we want to go a little bit more in detail, and we want to actually derive this region. That's what we want to do.
Even in continuous dimensions?
So So don't use dimension. That's an interesting question. You can promote this thing to be real. You can run the program, and some people, well, Dennis Karate and Liam Fitzpatrick, and I forgot who else is in the paper. They show that if you go to other dimension, this figure shrinks continuously with t. But if you take it as just a generalization, analytical condition of the bootstrap problem, because then physically I don't really know if we scattering fraction dimension. Maybe there is some sense, but I've never thought too much about it. Okay, good. So let's let's discuss one important constraint that we didn't mention yesterday, and this constraint is causality. So causality is the constraint that the signals cannot travel faster than light. And there is a very nice, which I could review it, but I chose to start. But just to remind that causality in the theory of signals, it really implies the Fourier transform is analytic in the upper half plane. This is like some omega plane, and you add some green function depends on t. Then you can derive some scattering. Well, it's like basically an S matrix for the signal, and this will be like analytic in the upper half. So, but this I will not explain this symbol model. It's contained in Gribov and in other lecture notes. People discussed this also recently. What I want to say is just that causality implies analyticity for the scattering amplitude. So let me jump directly to what is known. So it implies analyticity. And now I would like to comment on what kind of analyticity implies. So without doing too much, without going too much back, because you can take this story from the White-Mayer axioms, but that's not what I want to do. What I want to do is that I want to just start from the simple fact that our scattering amplitude, if I, let's say, fix S, and then I take cos theta, the angle, and I take it convex. So I take the angle convex, so I will continue in the angle. Then we know that T admits a partial expansion, which means just a Taylor series expansion where you don't have powers, but you have Legendre polynomials. Right? So there is like this 2j plus 1, 16 pi, fg of s. Then there are these Legendre polynomials. And Legendre polynomials, they converge in ellipses. So one old result of lemma, one very old result, is that this function admits a very simple continuation in an ellipse. And the ellipse has foci to -1 and 1, like cos theta that goes from -1 and 1, and then it stops when you hit the first singularity. And in our case, the first singularity is a two-particle threshold. Like a cut here, a cut here. This would be like the T-channel cut. This would be the U-channel cut. This number is when t is equal to 4. So it's really 1 plus 8 divided by s minus 4. This is this number. And it's analytic key.
Just a maybe pedantic question. So this is the analyticity J by J, or
no, analyticity of this.
But there couldn't be any issue like of using the analyticity of P, J inside the sum. I mean, I have any.
No, these are the polynomials.
Okay.
These are Legendre polynomials.
Okay.
And the statement is that when you expand in Legendre, so imagine if this were like just powers, this would converge in a circle.
Okay.
And then you stop when you hit the first singularity of this function, which you know what they are because they are given by unitarity.
I see.
Now, since you expand in Legendre, they are not circles, they are ellipses.
So I understand.
So, and this is what is called the small level ellipse. Now, there is actually another very funny result that is very useful in proving analyticity properties. which is that if you take the discontinuity of this function, if I take disc of t, it has the same expansion, j that goes to 0 to infinity, same thing, same thing. Here I pick the imaginary part of fj. Here I pick the same pj. But now remember, the imaginary part is bigger or equal than the absolute value squared. And for this sum to converge, of course, we have to be sure that the coefficients decay fast enough. Because the Legendre, so you can think about this Legendre polynomial as, so if this is z, this is z, you can think of them as like a z to the j. So they have to decay exponentially with j. So you can estimate roughly that they should decay like a to the minus j, at least. Then by unitarity, if this decays like this, then the imaginary part should decay like e to the minus 2j. So this should decay by e to the minus 2j because of unitarity. So this tells you already by I that the radius of convergence of this sum is larger. And indeed, there is this relation that it can be easily derived, but there is like a z large, which is like 2 times z squared small minus 1, where this is z small of the small Lehmann ellipse. And then in general, this z large, it's like this. Let me cover this region. Okay, so the imaginary part just converges in a larger ellipse. And if you want to understand physically where this ellipse stops, you can imagine that this stops when the amplitude develops a discontinuity in the discontinuity, which is like the double discontinuity, which for our process that we are considering here is given by the 3-loop diagram, this 3-loop diagram here, where it's changed 4 parts, let's say the Vichal or the Vichal. This gives a double discontinuity, and when you hit this diagram, this lambda singularity associated with this diagram, that's where you have this point and you stop converging.
In between means that you only produce 2 particles, and then when you hit this, you produce more than 2.
No, it doesn't mean that. It really means just that this. So naively, this discontinuity is like a larger radius convergence because the coefficients decay faster because of unitarity. You see, imaginary parts will equal the absolute value squared, or something goes like e to minus j. So this should be large. And it should be larger, and it should stop only when the discontinuity develops a double discontinuity.
When the discontinuity becomes complex.
Yeah, well, yeah, that's what I mean. Discontinuity develops
But this diagram that you've chosen is just because you're using on the factor.
Yes, because the charge of asymptotic states.
No, but
I'm being very specific.
That's the C2 that heard.
Yes, of course. Otherwise, you have like other diagrams that makes it stop even exactly. But that's good. Okay, so you see, we can say something about analyticity, but this is still far from saying that I don't know, this ample is analytic and SNT. And for instance, I can tell you like a funny anecdote that I learned reading some paper written by some Russian that in a footnote had a story that some other Russian told him that in the 50s, when Lehmann presented this result, Landau was in the audience, and Landau complained. And he said to Lehmann that his results must be wrong because the scattering is an analytic function. You cannot show that it's analytic in a smaller ellipse. It should be analytic anywhere. And then Lehmann replied to Landau, saying apparently, Landau, he's a big man, he needs big analyticity. I'm a small man, I'm okay with some small ellipse or something. So to say that, this is like a nice, cute result, but we want for more, much more. So just to give you a sense of how the story ends. So I will not give you the details from here to the end of the story, but just the end of the story. So what Martin proved, and this is literally the status right now, because I don't understand, I don't know anybody understands the paper by Martin. He proved that eventually, if you now take T, if T, I remind you, T is just, well, Z is 1 plus 2T divided by S minus 4. So you see, from this ellipse, I go from Z to T, and that's, I'm not with it's not a complicated transformation, Z to T. Anyway, in T, he proved that if you are in a region that looks roughly like this, some sort of potato, this potato stops at 4, the two-particle threshold with T channel, which makes sense. So you have a cut here. Then there is minus 28 here, which is a constant of nature, apparently, and it is what it is. And if you pick T in any way inside this region, so let's say we pick it here, then it shows that the amplitude is actually analytic in the product of this potato with the S-plane, complex S-plane, with cuts at 4, which is the two-particle threshold in the S channel, and cut at minus T, which can be complex, because this can be complex, it's not important. And this they use. And we are analytic everywhere now in the S-plane. There is this weird department here. Okay, so this is the status. If you want, I can also tell you the whole derivation, but it will take some time. But this is what has been proven.
Sorry, can you say again how do you go from the left figure to the right figure?
Yes, you fix T in any point here, and then the amplitude that fix T is analytic in the S-plane. And actually, the claim that he makes, which again I don't fully understand, is that it's analytic in the product of these two.
Because instead the first one, it was where it was analytic in T for
Yeah,
NES.
exactly. This was analytic in T for NES. And now you say you fix T, it's analytic in S in the of T. Exactly. So this should be understood as a product.
Means that I can also use S and then I'm
Yes,
analyzing.
exactly. Very good, very good. By crossing, you can also exchange, because we proved crossing yesterday. Well, we mentioned that someone proved crossing yesterday. So you can change, you can fix S here, this you can call it S, and then in T will have the same thing, call it U and so on.
No, I meant that I can also choose S outside the potato in S, and then I'm analytic with fixed S.
No, that's not how it works. No.
It does not commute.
No, it does not commute. No, because you have to, this like, you have to do the Cartesian approach. It's a 4-dimensional space.
Okay.
So, yeah, this is it. Anyway, so what you would like to have, actually, it's analyticity everywhere. So we would like to, to remove this constraint and be able to go everywhere. This is the dream.
And just to be sure, so this is the analytic domain of the amplitude written as a partial wave expansion for
all the amplitude.
Okay.
Then I use the partial wave, I induce Martin, Lehmann use the partial expansion to first go here, and then from here go here. So there is like some derivation, some proof.
Which is the difference from Bros, Epstein?
It's different, yeah.
Okay.
It's another, it's different. There's some overlap. Yeah. Again.
Okay.
People stopped thinking a long time ago, and
those are the regions of convergence of the partial. Right? That's where you want to use the amplitudes as a series, which are the partial. Otherwise,
Yeah, I can, yeah, just for you, I can give you like more details.
So this is because you have to use, dispersion relation, you have to use.
Exactly.
The partial rate expansion inside the dispersion relation and outside the dispersion relation, they have to be.
Exactly. So the argument runs, and I will anticipate something that I'm gonna say soon with dispersion relation, but the argument runs that now you want to analytically continue T by taking the integral of the discontinuity in T with some term. So then the analyticity will depend on where this discontinuity is analytic along the whole contour of integration. It means that you have to take the intersection of all these ellipses, because these ellipses depend on S. So for each S, there will be like different ellipses. The only issue is that if you just use the large level ellipse, when S goes to infinity, this right-hand side is, okay, let me write it here, since I know it. So the right-hand side, extremum in T, this is, let's say, 0. This is far away 4 minus S. But this extremum is like 256, not the constant domination divided by S. So when S goes to infinity, this ellipse shrinks to a segment. And you cannot prove anything. But what Martin proved is that there exists another ellipse, which instead has a right extremity at 4, so it's bigger. So then what Martin did was like to take the union of these two. So you take the union of 1 and 2, then you take the intersection over all S greater or equal than 4, and this union intersection ellipse is what generates this thing.
Then it's like we have one outside. Because once you project now the T, where you have to make sure that the partial rate also is valid for the one outside, we have.
Yeah, I mean, if you want to then resum the partial expansion, then you have to be again with the small ellipse. But this proves at least that the amplitude is analytic in the split.
But there's a surely conversion. You need to convert it.
No, the convergence, yeah, that's a separate. This is just about analytics. Okay, but okay, this was the one.
Sorry again.
No, that's okay. Okay, but just to say that the constraint we're going to use in the bootstrap is Landau analyticity. So we're going to build Landau, the big guy. So we call it maximal analyticity, which means that for us, we will take the amplitude analytic in S, T, and U well away from cats. So modulo cats. That would be like the working assumption for us. Waiting for someone to prove this. Any more questions? Okay. So, but this is not the only property that actually we are going to use. We still need something more. I'll do it here. So what we need is some statement about how this amplitude behaves at infinity. So what happens when I go here on this arm, let's say, when I go into infinity? So what happens? Now, another nice statement is that unitarity plus causality, they imply polynomial boundedness. And in particular, one can prove, and this I will do it probably in the last lecture, one can prove the first bound, or today we just mentioned the Regge boundedness, which is the statement that Regge bounded. The statement that when you take the limit for energy that goes to infinity of T at fixed T, which in our case it would be smaller equal than 4, or smaller than 4 strictly, and you divide it by a square, this goes to 0. So this is what you can prove. So the answer is not just polynomial bounded by any power, but it's bounded by power 2. Okay, so now I think we have all the ingredients. Maybe I want to mention something that's very cute, which is that if you wonder how much important is the mass gap in this case, it's important. That's a statement. But then, for instance, you can wonder for gravitational amplitudes what happens. No, because I like a lot gravitational amplitudes. And then there is like a nice result of Ziboedo and Kelianaring, which I like a lot, in which they prove that causality and unitarity plus the fact that at large impact parameter gravity is classical implies Regge bound. So you see, you just give like some more physical input to these constraints, then you can prove like very nice results. This is just a parenthesis, just because I like gravity. Okay. So now it's time to use these constraints together with unitarity to start shaping a little bit this region.
Sorry, Andrea.
Yes.
So you're saying these two guys show that also unitarity is causality, even in the massless case, you have the Regge bound?
For gravity amplitudes. Yes.
Okay. For gravity amplitude.
Yeah.
Well, particular case.
Well,
Not general ambiguity.
not general, because I think it depends a little bit. Because in gravity, you have this strong physical part that if you go to large impact parameter because of power counting, the amplitude becomes classical. It's classical scattering. And then using this input, you can prove something more. Okay. So now, before telling you how we do the analytic bootstrap, let me show you some analytic bounds on these coefficients. And the analytic bounds usually are derived using dispersion relation. The dispersion relation is not something I introduced so far. Well, I wrote it before on Ceramon, but now I will do it slowly for everybody.
Just for QED, then one would also expect that because you would expect classical electromagnetism.
Let me think. The 3D in 4 dimensions. It's marginal. Do you get the same statement? Large impact parameter. I'm not sure if it's just dominated. If you have to sum the well, I don't know.
I mean, the argument of power count is still there.
No, but the thing is that the gravity amplitude is interacting with G Newton. G Newton is dimensional field, and then the amplitude, has to grow with the energy. And if you combine these two facts, you see that the subleading, I mean, the higher order correction to the gravitone pole are suppressed.
Yes.
At large impact parameter. Now, for QED, I think it's a bit trickier. But I don't know by how. I need to check. Okay, so bounds. So again, so the CRM are these S matrix data. They're defined with the classic symmetric point. So they're defined in this nice Mandelstam triangle where you have like S, you have U, you have T. They converge in a nice polydisc whose projection on, well, these are even, no? Real T, real S, real U. So when you project it, it looks like this in this plane. That's some weird thing. And then we expand around this point, but that's not the only thing we can do. It's like the crossing symmetric point. We say that Lorenzo introduced earlier about CFT correlators. It's also Euclidean points. Very one-to-one correspondence. And let's say you want to write, so let me do something stupid. Let's say I want to derive an expression for C00. So what would I do? Well, I fix T equal 4/3, so I fix T equal 4/3. I know that my amplitude is analytic in the complex plane now, because 4/3 is here. So let me just show you that everything checks. So 4/3 is here. This is 4/3. So I'm inside the potato. Check. Then it means that I'm analytic in S. So that means that I can use Cauchy theorem. So I can draw the S plane and fix T equal 4/3. 4. Here I have like minus 4/3. There is a cut. The crossing symmetric point here it's 4/3, of course, like this. And I do Cauchy. So I take a contour integral here. So I write this as 1/2 by r integral over this contour of t at S prime with t equal 4/3, S prime minus 4/3 in the S prime. Then I block the contour. I block the contour, and what happens? You know, block the contour. I will pick up this cut. I will pick up this cut, and then there will be some arc at infinity. So the integrals here are nice. The integrals here, they will be what will they be? So I put 1/pi. That means the integral from 4 to infinity. This is a plus. This is minus action. Then where it comes from? It's an integral from minus infinity to minus t of the discontinuity of t times this S prime minus 4/3, and then it's the discontinuity in S prime 4/3. So the discontinuity cancels the 2i by definition, and here there is a minus sign just because by convention discontinuity is flipped on the other side, because the the plus I epsilon physical region in this chart becomes the minus I epsilon. So that crossing is actually doing this. That's why there is minus sign. Plus, there is something missing. Plus, a residue at infinity. Because in general, this amplitude does not decay. So there is a residue at infinity. Since here I'm divided by S prime, when I go to infinity, here I will pick S. Okay, now using crossing, what you can do, you can do a change of variable. So let me overdraw. Just cut this drawing a little bit. I can do a change of variable here. I can send S prime that goes to 4 minus S prime minus t, which is u. Then I have to change variable here, but because of crossing, this is the same discontinuity, it doesn't change. Therefore, this integral becomes simply 1/pi the integral from 4 to infinity, the discontinuity in t of S prime 4/3, S prime minus 4/3. Sorry. Is this, there is like 1 over S prime minus 4/3 plus 1/4 minus S prime minus 8/3. S prime minus 4/3. Sorry, S prime minus 4/3. No, it's the same. Sorry. No, it's the same. I wrote it less than it's correct. So it's like a 2, because this is like it's the crossing symmetric point. So the candle also will know about the crossing C. So this becomes S prime minus 4 in the S prime plus the residue at T. Okay, so using analyticity and polynomial boundedness and so on, we landed on this expression for C0Z. Okay, so what do we know about disk T for T equals 4/3? So what do we do? So let me write again the partial expansion, because this is like an important point. So what was the disk of the amplitude? So imagine it was like a sum, where J goes to infinity, there is some normalization, depends on J.
Sorry, Andrea.
Yes.
You're not missing subtractions. You are missing subtractions, so that's the residue of infinity.
Yes.
Yeah, but still the integral does not converge, right?
Sorry?
The integral does not converge.
No, converge. This is the residue at infinity. No, there's no problem with convergence of the integral. I'm just doing the most naive thing. I mean, of course, like if I choose carefully, I mean, if I do subtract the special relation, then this will become some low energy class. I'm, pedagogically, I'm just doing Cauchy, being sloppy and getting distressed. Okay, so there's this thing. So we said before that admits a partial expansion that converge because they're in the potato. So this is like S. Then there is Pj of 1 plus T is 4/3. So it's like 8/3 divided by S minus 4. And Legendre have the nice property that they are positive function when the argument is greater or equal than 1. These are positive because the imaginary parts are positive. Therefore, this function, it has some larger positivity, which I think is called absolute monotonicity. That's something. Well, I don't know, but maybe absolute monotonicity I should use for something else. But it's like very positive. In particular, it's positive for this T. For S prime on T, which is like between 0 and 4, it's positive. For all T and for all S, so for all T like here and for all S prime and so on. So it's a lot positive, this function. So this means that this integrand here is positive. So this is positive because I'm integrating above 4, so this never becomes negative. All this thing is positive. And if I could drop this, then this would be positive. But I cannot. But if you could, then this would be positive, and it would be stronger. But because of this ratio, we cannot. And that's the reason why this figure extends on the right and on the left. So the reason is because of this rigid bound. Okay. So now let me be smart instead. Let's not be stupid. Let me try to be a bit smart. And instead of writing the dispersion relation for C00, let me write it here for C10. Then what happens? Well, C10, I remind you, it's just the second derivative of the amplitude, because it's one of these matrix data. It's like the second derivative of the amplitude at S equals T equals 4/3. Now, I know how to write Cauchy for derivatives. So I know that if I want to do Cauchy for the derivative, I have to do, let's see, there is a 2, there is a 4, so it's a 2 factorial, is a 4, 1/2 pi I, and then I have to do the integral of T of S prime over T divided by S prime minus 4/3, but now at power 3. And now we'll not do the steps again, but because of this power 3 now in the denominator of the kernel, that arc at infinity here can be neglected. So that can be dropped. And therefore, this quantity becomes just 1/pi integral from 4 to infinity, the imaginary part of T, S prime over 3, divided by S prime minus 4/3 cube in the S prime. And now this quantity is positive. This quantity is just positive. And it's positive. There is like another way to say it is because it's dispersive. It's like, well, not all dispersive quantities are positive, but dispersive, I mean, for sure, like if it's not dispersive, it cannot be positive. So this is dispersive. So this is the terminology. Dispersive, it means that these quantities can be written as pure integrals of the imaginary part of the amplitude without any additional data. And in this case, it's positive. And that's the reason why when we go to this side, we can draw all these part is X2. No, positivity alone, we can already cut half a plane. Infinity to half infinity. So, okay. So, but to obtain this, to obtain this this region, we need to deal with this residue at infinity. With its residue infinity. This residue infinity turns out also to be a real quantity, so like a real. If I write this dispersion here, it's like a real thing. It's a real number. So you see this real number, it already tells you that you don't only need to control the imaginary part to get the bound, but you also need some control of the real part. The control of the real part comes not from positivity alone, but comes from the full unitarity. So the control of that real part comes from 2 times the imaginary part of J greater than this.
Can I ask a question? So do I understand correctly that the residue infinity, I have it if the full integral on the first line goes like 1 over s at infinity or not? The first line for C00, right? When do I have a zero contribution to this residue at infinity?
I think that by unitarity, okay, there are 2 options that now, like, for me, they're equivalent. Maybe it's only 2, because I so I was like a bit far. Okay, there are 2 options. Like, either I did discontinuity, like, decays faster than the real part, so it could make this integral converge. That's one option that now comes to my mind.
Okay.
Second option, it's just, okay, it's like 2 integrals, and they are not absolutely separately converging, but they got the sum converge. So of course, this number is fun. So,
But I mean, it could go even worse, no? Because I thought you said that t can go like s squared.
yeah.
So if it would go like a square, it would be need more, even more power.
Because no, it has to be smaller than a square.
Yes.
And then because of crossing symmetry, we can only have constant. We cannot add power s.
Okay. No, understand. Okay. So that already is on the verge of convergence.
Yeah, that's already on the verge of convergence. Therefore, things can happen. Discontinuity decays faster, so this might converge alone. But if it's not, I apologize. Then it means that you have to take these 2, sum them up, and then the sum will converge.
No, I was confused by s squared. Okay.
But, if I do subtract, then I don't have to worry about it.
Probably in green light, you have the problem.
Yeah, that's exactly the point.
The problem is small.
Exactly. And but if we do things correctly, and we will do it now, then you get the polymer on here. So if we do things correctly, we get. Okay. Just a comment about the real part before I forget. Why we need to control the real part? This inequality does it because, let me draw it for you. This is just a circle, but it's sheet. So it's this circle here. This is the imaginary part of J. This is the real part of J. An imaginary part just means that this partial, the imaginary partial must be positive, but full unitarity actually must be contained into this circle for each s and for each j. Okay, so that's why we have like powerful constraints that we can just say something about these C0s. Okay, so this finishes the first part. Now we can do the primal bootstrap.
So this is what they were saying, that the 8 point was like large in C, because it's purely real.
Yeah. Okay, so now we can do the primal bootstrap. And with primal bootstrap, we will forget about this potato. We don't care about the tip or forward tree inside the potato. We don't, we don't care. We are gonna be just free. And the idea is to not be a. Yeah.
C00 this was a known manipulation, but C10 was.
No, C10 it's kosher. C00 was just like manipulation to see that it fails the argument. That's why you expect that you have both branches, positive and negative. Okay. So in primal bootstrap, the simple idea is to not be afraid of full analyticity, don't be afraid of functions of many complex variables, and just harness the power without any fear. That's the primal bootstrap. So primal bootstrap. And the idea is that, well, when you want to write an analytic expression, it's always nice to work in circles and do Taylor expansion. That's the idea. So what you do, you take each variable S and you map it to a disk. Now, what is the operation you want to do? Is that you want to take your space, which you can think of it as the product of three cut planes. So your actual space is, you can think of this like this product of this cut plane, let's say S, times the same thing in T, times the same thing in U. And see, I'm doing something strange. I will tell you in a second why. So I'm taking your product of SP and U, like if they were independent variables. And then for each of these cut planes, I do a conformal transformation, just a Minkowski map, and map it to the unit disk. We map it to unit disk, and the map is in general 4 minus S0, it's like minus plus. There are 4 square roots. And then it's like a cutted 4. Then I fold it like this, and this becomes S0. So this is what we call row variable S, which depends on the center, which is this S naught. S naught can be taken, let's say, here. This can be S naught. Then it will be mapped to the center. Then if I take S equal to 4, I go to 1. So this will be S equal to 4. If I go to infinity, I get minus 1. So this is infinity. Then the cut, well, the cut is mapped to the boundary of the disk, and in particular, the cluster epsilon part of the cut is mapped to the upper disk, sorry, on this side. It's mapped to the upper part of this. And so now, my kinematical space is the product, so let me call this D. So my kinematical space now becomes product of ds times dt times du. But this is too large. So what we do is that we mod with crossing. That's the only thing that we do. What it means in practice means that something very simple. It means that we do a Taylor series expansion in SP and U, and then we impose that U is 4 minus S minus T, and that's it. And this gives you the most general function of 3 complex variables with cuts and compatible with cross. So let me do the we call it transfer, but it's actually an expansion, so that I can, I can send this sum to infinity. So say I can do n and p that go to infinity, and then I can write some coefficient. Well, not c, alpha. N and p. Then I have these 3 variables, rho s to the n, rho t to the n, rho u to the p. And these coefficients are totally symmetric. These coefficients here, which are 3 variables, are totally symmetric in n and p. Since they are totally symmetric, it means that you can exchange S, T, and U as you wish. And since each S has been mapped from the cut plane to the disk, it means that this function has cuts in S, T, and U in all the lines. So this is the whole idea.
But S0 is quarter, that's what I mean. No,
it can be anything. You can take it forward 3.
okay.
And if you do it, actually, let's do it. Thank you. Let's do it. It's not equal forward 3. Then it means that C00 for us is alpha 0, 0, 0.
Good combination.
Yeah, it's nice. Yeah. You don't have to take some linear combination, whatever, just on your nose. Yeah. Okay. Now, perhaps maybe some technical point is that of course, this is not an analytic continuation in trivial. It's an analytic extension. It's called analytic extension. And it's an extension and not a continuation because it's not unique at all. And it's not unique because of momentum conservation. Because you see, momentum conservation tells you that you can add to, so if you had an amplitude like a pure function of the complex variable, then I could always include polynomial form x minus p with the end. And this would give rise to some gauge redundancy. So you would some gauge symmetry that you have to mode out. Okay, so because of this, this is like an extension, and that's why we mode by sorry. Oh, because it's symmetric. Sorry. Made a mistake. This is like mode by momentum conservation. Crossing is already symmetric. Okay. Right. So this is the expression that we start. Now, this expression is the beautiful property that satisfies all the special relations that you want. Satisfies, for those of you that know Roy equation, let's say satisfies automatically all the Roy equations, set with equations, and there is the only thing that you need to impose is unitarity. That's the only thing. A unitarity, it's a constraint that will act on the alphas. Because no, the only thing that you have to do with these answers, or with this function, is to define fj, let me call it t ansatz for standard reason. It will be like, the integral in z, I put the legend, z, I take my t ans, function s and z. And this, if you want, it becomes sum over n and p that go to infinity. That will be my alphas and p, and then there are this projection, ejt, and then this rho s to the n, dot t to the n, u to the n, u to the p. So the partial waves are linear. So this is very important. The partial waves are linear with these coefficients. So everything is linear, doing only linear operations. And these integrals can be computed analytically, in this case, because it's a very simple function, or numerical. So this you can compute them, you can store them on your laptop, and that's what the code does. And it calls them n and p. It depends on j, and compute them for each s. Then you take this thing and you plug it into the unitarity equation. So you have to be sure that these fj are inside the circle. So let me write the formula for the circle again. Fj squared. Now let's see if I wrote it in this notation or this notation. So I need for this one. Let me write for this matrix. So unitarity for S, not F, it's just absolute value square of F is still smaller than what I want. And again, Sj is just 1 plus R rho Fj, and Fj comes from here. Okay, so okay. And now we use this equation that this constraint is equivalent to this matrix here. It's equivalent to the matrix which is 1, 1, and then I include minus imaginary part of S, J, 1 plus imaginary part of Sj, and then I include real part of Sj, and real part. So it's like symmetric. It's a nice symmetric matrix. And this condition is equivalent to imposing that this matrix is semi-definite. And now we have like a nice SDP problem. And that's where the bootstrap. So this is what the bootstrap can do. Bootstrap can do. well, bootstrap, I should say SDPD. This is what SDPD can do. Okay, so now how do we derive the potato? We derive the potato by maximizing. So let's say I maximize. So what will be my problem? So the problem will be to maximize C00, which is actually alpha 000, subject to those constraints. So let me call this constraint unitarity. So I call it Uj of S. And this has to be subject to Uj of X. Semi-negative positive for J that goes from 0 to 4 infinity, and for S that is greater or equal than 0. So if you do this, you will find this point. Sorry, and the maximization is done varying over the alpha. So this is like done varying of the alpha ABC.
So for those of us who know about SDPB, can you explain that a little bit? Because here, myself and my students are not familiar with.
Yeah, SDP.
And you're talking to people who
No,
go.
let's say that it's a black box.
Okay.
It's a black box that you can download. You can install, asking codecs how to do it
That's what you provided. Yeah.
right, on your machine. Now, what I provide is the code that in the end prints for you the command that you have to run. Right? So if you have SDPB, you copy paste those commands and then it runs. I'll show you how it runs on my own in a second. Yeah. But this is the whole thing. Now, two quick comments, and then I really need to go to the. But I start with 5 minutes late. And so, two things here is that first of all, this infinity here is dangerous because you don't want to sum over infinite terms. So you want to truncate here. So it will be some n max parameter that tells you how many terms in the sum you want to put. And then this infinity also is dangerous here. So you want to put an L max here. And also these continuous variables sometimes can be handled. In this case, it's very painful to handle. So this becomes S grid greater or equal than. And this is how we discretize this problem to put it on a. Okay. Yes, we maximize. When you maximize, you get the point. Of course, like you have to. When you reach the real maximum, the optimal value of C00, you are sure that you excluded all the spots. Right? And this means maximize C00. Now imagine that you maximize minus C00. So I maximize minus C00. And then I get to this point, and it means that if I truly maximize, all the way to convergence, I'm excluding all these points to the left. But then in general, what is smart to do is to find what is called the supporting hyperplanes of this figure, which is like a fancy name to say that I want to maximize linear combination of C00 cos theta plus C10 sin theta. And what is this theta? This theta is basically the normal to one of these planes. So if I pick this theta, let's say, I will shoot and then we find the point on the boundary whose tangent has this norm. And I will exclude all this point. So, for collecting all the thetas, I can, sorry. Not to all state. Okay, so now yeah.
One curiosity about the discretization of the grid. Since STPB works with polynomial,
Yeah.
using polynomial for the imaginary part of SJ,
Uh-huh.
and then finding the real part through dispersion relation. Is it numerically challenging then construct our observables then?
You could try, but there is like this integration that you mentioned, that you have to integrate the imaginary part to get the real
So
part.
it is not linear anymore.
No, it's not that it's not linear, it's that you have like, you have many integrals to do.
Okay.
Many integrals to do, and then,
So what I gain here, I lose.
yeah, you gain, but then you lose, so, yeah. It's cool.
How do you implement this, how do you remove, let's say, that space in the mental conservation in this process?
Yeah.
Maximum is.
Yeah, it's very simple. So just, U is 4 when you stand by yourself. One thing. And then there is another thing that is very important. Right?
Can you implement that in your?
You have implemented this in your answers too. So thank you for the question, because it might be something I forgot to say, that this triple sum has some gauge redundancy. So this triple sum, so you can either fix the gauge, or you can go to some smart gauge, which is basically remove one variables and then see the price. That's what the code does.
So
Yeah, if you do like this, then you get rid of this. Yeah, that's what we do. It's literally a choice of gauge. Close. Okay, so the notebooks are here. Okay, so you get all these notebooks here. There is a README, which if it's not updated, tell me, I will make it more clear. But the thing is that if you download this folder, and then you just run this, so there are like a few files here. There's a library, SDP, which is the library that you need to write the input file of SDP. There is this Z2 bootstrap for this import threshold option.wl, which is the engine. It's where the ansatz and everything is in. And then there is this Z2 event symbol, which is just a wrapper to run SDPB. And this is a notebook that I implemented to do some data analysis that we can do. So we can maximize the amplitude live, then we can see partial waves in Unitarity, we can see some. Okay. So let's say I downloaded my library. So tabs, I use a school, notebooks. Okay, there's also some junk, but that's like junk. We will not have junk in this folder. So I downloaded everything. And then if you run this, so we say we take this 0 run Z2 event simple. Now, if I run it, so let's see, I want to comment this. So I think in the version I will commit now, because it's something I forgot before, there is some final line that this finishes the PV run. It's like some cleaning lady, and sorry, it's cleaning, and sorry, it's cleaning, and it will just erase all the things that usually I do it. It's me that take it. Yeah, I'm saying I'm cleaning. Be very specific. It's no, okay. Was like my South Italian vibes. So. And
You can continue and make it worse.
Okay. So okay, before going to the thing here, it's 000 even. Yeah, in London they already complained students that have to work on it. So you can run this package. This package, even if you run it on your laptop, it will download 600 megabytes of integrals, which are the ones that I think it's more than enough for you to reproduce the most complicated amplitudes that are in some of my recent papers. So I really give you everything. Yeah, could give less, but
Quindi they're computing those intervals and delta in the partial way.
they're already computed.
Yeah.
And they're in this folder. So the code will download the folder, will unzip it for you, will put it in the folder, and that's it.
How long did it take you to compute it?
Not much. Maybe you need a cluster. If you do it on a cluster, it's because it's many integrals. May computed way more integrals that you might need for some games. I mean, it's yeah, there is everything. Maybe I will do.
Very nice, thanks.
Yeah. So anyway, it's like a lot of jargon that Codex wrote. It's just management. But then the thing is that in the end, it will print for you this part, which is the important part, because then you take these commands here. And there are two commands to run SDPP. One is this PMP to SDP, which just converts your input file in JSON to some input optimized format. And then there is this other command here that runs the song. So you use to take a copy. I go here. I paste. See what happens. Okay, done. Process. Then I copy this part. I paste. See what happens. So it starts. So it starts, and what happens here is that there are many parameters, but what you want to look at these two numbers. So when these two numbers agree, then your solver finds the optimum. And you see now it's like 10 to the 44, that's 1.4, so they're still far apart. But now if we wait a little bit, it will, then we get, no, sorry, that's the duality gap. So 10 to 12, 10 to 20. Okay, we are getting closer. Can you see? Yeah. Okay, see, now they are getting closer. 2.65, 2.65. It finished. So why did it stop? It stopped because these two numbers, which I would need to explain you how the interior point method works, but these are the primal and dual solution, because what this algorithm does is that maximize and exclude from the other side. So when these two numbers meet, then you find the optimum. And this difference is duality gap. So I say when difference more than 10 to the minus 12, you can stop and happy. This is like some parameter you can think with some gradient descent. So it's like some mu that makes you go towards these two guys meet. And there are like a bunch of other stuff which takes some time to explain. But these are the most important part. So now it did it. Now I can clean, and this part is a bit involved just because okay, it's a setup. You can choose whatever setup you want. I do it automatically, so I run this thing. Okay, so now from the output file of the code, extracted some numbers for you, which are the alphas, which you cannot see here anymore. So now the code extracted the alpha ABC. And now we can open another notebook, which is this analyze data, which is the one that you can here you have a lot of freedom. So there is some configuration. I will tell you exactly what is this configuration. Or maybe next time we can keep going. So this something that I should something I should tell you that in the runner you have to choose the parameters. And I forgot to tell you that that there was this Nmax, Lmax, Sgrid, and so on. So here is where you choose Nmax, Lmax. The grid you don't choose, that I choose, and theta. So the theta is the angle where you shoot. So here we chose theta equal to 0, which means like maximizing C00. and I chose L max equal to 2, so I bound up to spin 2, and I chose L max equal to 2, which means like constant plus rho squared. Very small small function. Okay, so this you have to tell the code. Then there are some more fine things because it's a bit sophisticated. Okay. Okay, so this run it. Now, these parameters have to match here, of course, because here I'm looking for the file that they produce with max equal to 2 and max equal to 2 and t equal to 0. Means this one, and it's in the folder. So, okay. Now we can read the solution. So, okay, this is already read, it's already read it. You see, it found these parameters. So it found alpha zeros, number alpha 1, alpha 2, alpha 1. There is a th. There is a th because there is an option on top of this code, which tells you if you want to include a threshold bound state term. What is the threshold bound state term? Don't be scared, it's just one thing. It just means that together with alpha ABC, it adds a term with this coefficient th, which looks like 1 over square root of s minus 4 plus t plus u. And this term with the square root is a singular term that sometimes can accelerate the convergence of the problem because it's like the singularity is admissible by unitarity. Okay, so then you can run this part. And you see, it's beautiful because now you can plot the real and imaginary part of the amplitude in S and T. And you see, this is like the real part, and this is the imaginary part, and this triangle that shows up is the Mandelstam material. So you see, it's very nice. You can rotate, you can see that. Beautiful. Here I did it in the variable state there. It's really in the variable. It's fully easy.
Andrea, should we wrap up? Maybe we can add some more links.
I finished.
No?
No, I really finished. That's it. That's it. Because then you can just plot the this already plotted the partial waves, and here you see that green line is unitarity. So these are the SJ, the starters what we got in one. So green part is like the unitarity bounds what we got in one. There is like blue is the real part. This is like the imaginary part for this problem. This is the phase, if you want, the phase shift. Then you can plot the higher spins, you see they are boring. And and then okay, next time we will study these amplitudes and we'll understand how to extract physics from these things. But okay, this is the how it works. So yeah,
Okay. Let's thank Andrea for the. Now I'm not sure if